Hello, my name is Tina and I'm going to give a short presentation on RSA key extraction via low-bandwidth acoustic cryptanalysis by Jenkins, Shamir, and Tromer. There have been many attempts throughout history at creating ways to encrypt messages to communicate secretly. A method that is commonly used nowadays is called RSA. But there are always people who will try to decipher messages that are not meant for them. RSA is hard to crack, and when encryptions are hard to crack, people tend to try to go around them and use side channels instead. A side channel attack uses information gained from the physical implementation of the crypto system. Examples of side channel attacks are power consumption, electromagnetic emissions, timing, and audio. So, you know that annoying high-pitched noise that computers make sometimes? Well, this sound has been called coil whine, but it's also made by capacitors. That sound is more than just a nuisance. It can actually reveal what the computer is doing. In 2004, Adi Shamir and Aaron Tromer wrote about how they were able to distinguish RSA keys only by analyzing these acoustic emissions. At that time, it was not clear whether this information could be used to extract the secret key. However, 9 years later, in 2013, after having joined forces with Daniel Jenkins, they had found out how to extract the key. But let's start at the beginning and explain what an RSA key is. The RSA crypto system was named after its designers, Ron Rivest, Adi Shamir, and Leonard Edelman. By the way, this is the same Shamir as we were discussing before. The system is based on the idea that you can have two keys, one to encrypt a message and the other to decrypt it. The encryption key is public, and anyone can know what that is. But the decryption key is secret, and only the owner can know it. The public key consists of two numbers, N and E, and the private key consists of three numbers, P, Q, and D. P and Q are two large randomly selected primes. We'll construct N, the first part of the public key, by multiplying those two primes. To get E, we'll first multiply P minus 1 and Q minus 1, which we'll call phi of N. Then we'll select a random number such that it is greater than 1 and less than phi of N. And this E and phi of N are coprime, that is, their greatest common divisor is 1. Now we have most of our private key, but are still missing D. D is the inverse of E, that is, E times D is 1 modulo phi of N. So now we have the public key, N, E, and our private key, P, Q, D. The system works because it's really difficult to factor large numbers. A message M is encrypted by raising it to the power of E modulo N. A message is decrypted by raising C to the power of D modulo N. But a quick way that is used by many algorithms is done by splitting the problem map and then obtain M by using the Chinese remainder theorem. This way is about 4 times faster. What Jenkins, Shamir, and Edelman essentially found out is that they could record the sounds made by a computer while decrypting messages, and from that recording they could distinguish P and Q. The recording could be done from far away if a high-quality microphone was being used, but they could also use a regular cell phone to do the recording. The cell phone just had to be placed close to the target computer or about 30 centimeters away from it. If we look at a spectrogram of such a recording, it looks something like this. Here we have a spectrogram of RSA key decryption made by GNU-PG. The 5 arrows represent 5 decryptions of the same message using different keys. For each decryption, we'll see a line, a short break, and then another line at a different frequency. This is when the exponentiation modulo P and the exponentiation modulo Q are happening. As can be seen here, the keys do not look the same, but are distinguishable. More importantly, P and Q are distinguishable, so we now have information about the primes that we should not have. Let's hear what this sounds like after the sound has been adjusted so that it is audible to us. Here we have 5 different keys, and for each of them we could hear P and then Q. Let's hear it one more time. Okay, fine, we've heard the keys, but this is just noise. How does that tell us what the actual primes are? The implementation that Jenkins, Shamir, and Edelman focused on was GNU-PG. GNU-PG is an implementation of the Open PGP standard and is used to encrypt data and communication. They also used Enigmail, which is a plugin to the Thunderbird email client. It automatically decrypts incoming emails using GNU-PG. How convenient. So what they did was that they sent a whole bunch of cleverly crafted emails to the target computer and recorded the decryption. To decide on how to craft these emails, let's have a look at the algorithm being used. Here we have the function modular exponentiation that calls car_super_mult, which calls basic mult. Basic mult is what we're going to exploit. Since it's the innermost loop, it will be repeated many times, and the small effects we have in there will have big impact on the whole. And here we can choose whether we take the if or the else statement. GNU-PG processes the bits of the exponent from the most significant bit to the least significant bit. Now we're going to expose Q one bit at a time. And when we know what Q is, we can easily figure out what P is, since we already know N, which is P times Q. GNU-PG generates RSA keys such that the most significant bit of Q is 1. Knowing this, we'll send an encrypted email that has 1 in the first bit, 0 in the second, and the rest is all ones. Listening to the computer, we're going to hear whether C is greater than Q or less than Q. Now we send this message to the target computer, and we hear that C is greater than 1. This means that this bit of Q has to be 1. We'll repeat the process. And now, C is smaller than Q, which means that the third bit of Q has to be 0. We can go through the rest of the bits like this until we know every bit of Q. If we are using a 4096-bit key, so P and Q are 2048 bits each, this process takes about an hour. So, what can we do to prevent this? Let's have a look at some ideas. One idea is shielding. This has been used on shielding electromagnetic waves. But the sound will still be audible, so this won't help. What about adding noise? It might seem like a good idea, but since the sound is very high-pitched, it can't be filtered out. And you could even record multiple machines at the same time and distinguish between them. Parallel software load will affect the frequency and move it so it actually just helps the attacker. Soundproofing should work, but it's not practical, since the laptop will always need to have venting. Now, let's have a look at some more useful ideas that have been used to patch this problem. Ciphertext randomization will make the modular exponentiation routine random and help prevent the attack. Modulus randomization will randomize the modulus during each exponentiation, and the modulus can even be changed to various multiples of Q during the exponentiation loop. Ciphertext normalization will also help, since previous implementations allowed for the ciphertext to have leading zeros, which helped the attack. But this is easy to fix. So how vulnerable are other algorithms and cryptographic implementations? The researchers say that this is an open research question. Other systems may be vulnerable to acoustic leakage, although it may not be possible to extract secret keys from it. This remains to be seen. Thank you.